14.1, we define what we mean by vector value function. So we're always going to define our terms. The first important thing. So when I reference a vector value function, I will give you the heads up. We're covering a lot of volume today, so try to keep up with the pace. This is going to be essentially a vector R, where the parameters themselves are equations with respect to some external parameter. Okay, so x varies with some external parameter t, y, the y coordinate or the y parameter is varying with respect to some outside thing t, and then z with t. And so if you ever heard of the term parametric equations, that's kind of what's going on. So you can think of it as a vector value function that's having three parameterized equations, or you can just think of it as a vector where the components themselves vary with some external parameter. All good? Sure. Okay, so that's what we mean. A vector value function, it's just going to be a vector with functions in the components. So yeah.
This is a t, right?
Yeah. Yeah, with respect to t. Okay, and then I'll show you a notational convention, and then we'll define what the domain of this function is going to be. So if we have let, that's our word we use that. So let R of t. And we're going to now use, instead of the x, y, z, it doesn't really matter what we say. So I can say f of t, g of t, and h of t. This will, I think, more conventionally common, at least in your text. And then recall, I want you to remember, since these are just components, you can, if you wanted to, represent your vector value function by writing it in component form, right? This would be j, and then f, g, h, t, and k. And the reason why I like to distinguish between this is because there's going to be a very common mistake that's going to lead to confusion, is that it's all notational. Vectors need arrows more now than ever. Again, I'll give you the fair warning now, just so you can't say I didn't tell you. If you write a vector and there's no arrow over it, I will read it like a scalar and I will think about it accordingly, okay? This is going to matter a lot, because do these have arrows over them? No. Oh, so are these vectors or scalars?
Scalar.
Right, these are scalar quantities. Sure, it's a function, but it's outputting the scalar. This is outputting a quantity, but what kind of a quantity?
The vector.
All right. So can we assimilate vectors, just throw in scalars when we feel like it, and then oh, we're back to vectors, and oh, now we're back to scalars?
No.
No, it's going to break all the rules. Okay. So this is going to start to matter. That's why it's important to recall that when you see this component form, that this is really saying scalar part, and then it's a vector component. Scalar part is part of a vector. Scalar part is part of the vector. Okay. So don't forget about that. Don't be sloppy on notation now. If any time to develop habits, develop them now. And then we can define the domain. So if this is our vector value function, then the domain of R, notice that it's a vector, is the largest set of values, largest set of values of t, that parameter, the parameter variable, on which all of f, g, and h are defined. And that's just kind of common sense. We're putting into a definition something that we intuitively know to be true. If this was, say, something like, if f of t was 1 over t, well, you can't plug 0 into that because that's undefined. And so we got to make these considerations where we want to take as many values of t as possible on which the FG names are going to be defined. In the more set theory language, you can think of it as intersection of domains. But if that's more abstract, you just prefer to think about it like in the words, that's totally fine. It's the same idea. Okay, so here's kind of what we're used to seeing is something kind of like f of x is equal to, say, like sine of x, right? And when you graph a function like this one's the one that starts at the origin because it's sine, so it starts by coming up, and then on the other side it's going the other way. So we would think of this as how we would then graph y is equal to f of x with x down here. Now, that's because we're giving it structure. This is on the horizontal axis, and then what's going to be output is represented vertically. It's a little different with a vector valued function now, because we can exist in 3 dimensions. So we're tracing out curves instead of necessarily drawing a function out in 2 dimensions. So here's a classic example, one that you're going to see so many times that you should just start memorizing it now. It's going to be the circle. So the x component goes with cosine. So cosine t. Y component goes with sine. And then we can just choose for the z, I'll just choose a constant here. Let's do 5. Doesn't really matter. And then now notice I'm going to specify a very specific range for the parameter. I want 0 less than equal to t less than equal to 2 pi. So this means start, end. And that's really important because the way that we trace these out, it's going to matter. Notice that this doesn't really have a direction. You can just put the graph on the page and that's what it is. But with parameterization, because you have a starting point from the parameter and then you end somewhere, then this now has a direction. So let's see what this would look like. This is our x component again. This is our y component. That's a z component. So what we've got is essentially a circle, right? If we were to just look at the x and the y components. But then what have we done to it in the 3rd dimension? What does that phi represent?
A constant.
Yeah, it's a constant. So we kind of brought it up into the z-axis by phi. So here is our x. Here's our y. And we're going up z. So if this is phi, right there in z, and then we have essentially a unit circle going on, but up at this raised elevation. So we've got this circle, it's going around. Oh, good question. Well, as t would increase from 0 to 2 pi, that's exactly what would be happening. And so this would actually become not flat anymore, but the height is going to increase as time continues as this goes on. So this would start to emulate something more like a spiral, slinky or something.
So the space between each line is defined.
Well, it is defined. It's defined by the parameter z. And so you could always determine exactly how high you will be at any given time because you have that scalar function for the z component. And that's true for every single component. So you want to know where you're at, where your x coordinates at any given time? Well, that's kind of what this is for. It's just going to give you that formula for each one of these components. So it's basically like 3 functionings happening at the same exact time, depending on how you want to look at it. This is going to have a very specific direction and also this parameter. So the thing I wanted to point out is if I had, say, changed now the 2 pi, and if I take out the 2, okay, well, how does that affect what visually is going to show up?
Half circle.
Right. It doesn't go all the way around. It's going to stop at pi. Now, if I increase this 4, okay.
It's gonna do it twice.
Right. Now, is it visually going to be the same as 2 pi?
Yes.
Visually. Is the actual, is the motion of tracing it out the same? No. So you're going to repeat that tracing motion twice, even if the visual output with the trace looks the same. So that's the only this is the main caveat when we move into vector value function. Consider the fact that now we're not looking at something static in R2, but we're interested now in how it's changing, exactly how it's being traced in space, not just the final resulting shape. Does that make sense? Okay. So then we can start doing some calculus on these things, and it's thankfully really, really intuitive. So essentially, everything that we're talking about today, you already know in the sense of the mechanics. So I'll just show you what you're allowed to do and what you're not allowed to do when translating it over to vector value functions. Okay. So we're gonna define at least what we're allowed to do to notation. So if we take a limit, that's kind of the first think about Calc 1 for a second. You started with limits, and then you use the limits to progress to what concept? Derivatives. And then after you work through derivatives and stuff with the applications, then we'll put it. So that's basically what we're gonna do. We're gonna recap those three main things with vector value functions. The limit as t, which is a parameter going to some value a of a vector value function rt, is going to be equal to L. Notice that L is a vector now. So you can't spit out a scalar in this event because we've got a vector value function limit. So we're going to hope to get a vector out. And so this is going to be true provided that the limit as t approaches a of the difference between r of t minus L goes to 0. Now, why is that a scalar? Why did I not make that a 0 vector?
Because you're only concerned about the magnitude.
Yeah, say it louder for the whole class. It's important.
Because you're only concerned about the magnitude.
The magnitude is what we're taking the limit of here. Vector by itself is what we're taking the limit of here. So vector is going to go limit to a vector, but this is a magnitude of. So this is now going to be a scalar. So it involves vectors. We're taking the difference of those vectors, but that magnitude is what that's going to approach 0. So all that really means is that essentially, if you take the difference between what you're supposed to be approaching and your vector value function, you should end up just on the same point. In other words, the 0 vector, which has a magnitude of 0. So that's how they present vector value functions with limits in the text. So here's an example to prove that you know this. You just got to get familiar seeing it. So if we have the vector value function r is equal to cosine pi t and sine pi t plus e to the minus t, and we'll do this for positive or non-negative values of t. So it's kind of like a physical environment. You can start time at 0 and then move it forward in the next experiment or something like that. Okay, and then let's take the limit. So let's do the limit as t approaches 2 of r of t. So if you see this, first thing you're going to want to do is basically be like, okay, well, that means I'm going to be taking the limit of all these different components. So the limit t approaches 2, let's plug in what this vector actually is. It's cosine pi t sine pi t e to the minus t. But what this means is that we're going to take that limit specifically for every single component. So you can really just think of it as 3 limit problems that has turned into 1 question. So it's really the limit as t approaches 2 of cosine pi t as the x component. So what's the y component going to be? You could just shout it out.
Sine pi t. The limit is
Right. The limit as t goes to sine pi t, and then the limit t approaches 2 of the last function. So
e to the negative.
the minus 2. And then now Calc 1 takes over. So do you see how it's just, we're back to Calc 1. Everything is going to be a roadmap. All roads lead back to Calc 1 today. So if you know your Calc 1, this is going to be the easiest chapter of your entire life, basically. Because you're just reiterating everything you've already practiced and memorized. So here, since cosine pi t continuous at t equals 2.
Yes.
Yeah, it's actually continuous everywhere, but that's okay. So 2, we can just plug it in. Cosine of 2 pi is what? Good. And then is sine pi t continuous everywhere?
No.
Where is it discontinuous?
Oh, my bad.
Yeah,
I
no,
think-
sine,
I
yeah,
think it's
sine
gonna
pi
be
t is
0.
going to be continuous everywhere. So then 2, we can just plug it in. Sine of 2 pi is what? And then is e to the minus t going to be always continuous?
Yeah.
What's the consensus? Yes? Is it can we just plug it in?
Yeah.
Okay, good. So then we have e to the minus 2. You know what's slightly ironic is that with Calc 3 students, you've seen some stuff by the time you get here. And the hardest thing Generally, it's the high school level part of this class. So brush up, and generally, brush up on your algebra, brush up on your function properties. The, trig, the fundamental trig functions, exponentials, logarithms, linear equations, quadratics. Just know your stuff, that you were supposed to already know, because it'll make everything much easier to go. And also the kind of examples that you will do are going to go 10 times easier. So you can set yourself ahead just by knowing high school math in a Calc 3 class. It's really, really fantastic. Because otherwise you'll end up like pure math professors in the future who can't do arithmetic in their head. Like the scariest thing for me is to subtract by 9. If you want, anyone can give me the craziest theorem, I'll fight through it. But 17 minus 9, I'm convinced it's 7. No one can change my mind about that.
If T were to go to infinity, how would you then, what would the result be? Would it be infinity, 0?
Very good question. Cosine and sine, this is interesting discussion because cosine and sine are bounded. So the limit doesn't exist because they're an oscillator, they're infinitely oscillating. So they don't actually approach anything.
Okay.
This would approach 0, but these don't. Well, let me think about that. So this would approach. Yeah, but this one wouldn't.
So it would be.
The limit would be undefined. Yeah.
So if we were to encounter a property like that, undefined, 0.
No, the entire thing is undefined. The moment you have one component that's undefined, it's all lights out. Yep.
And then let's say it was a scenario where it ended up at infinity 0. Could you write it as infinity 0, or would it just be?
Well, that assumes that infinity is a number. And so what you do is you treat that as an indeterminate form, and then you perform other calculus 1 skills like L'Hopital's or something to try to resolve the issue of having those. Yeah. So it's the same thing as like if you were doing a limit back in Calc 1, and then if you were to directly substitute like with rational function, then you get 0 over 0. That's obviously not an answer. That's indeterminate. And so that's an indication that you need to do some other extra algebra work or something, or L'Hopital's, to find what the limit actually is analytically. But not all limits exist. So don't force a limit to exist if it actually doesn't exist. That's an important reminder for all of this. Because I have made some silly mistakes in the past trying to make a limit that didn't actually exist. It didn't work. So I was close to gaslighting myself that I had done it, but I was nowhere close to actually accomplishing it in reality. Yeah. Okay, so most of you have probably forgotten the definition, the limit definition at least, of the derivative. So I'll remind you. Because it's essentially analog to vector value functions. So r prime of t, that derivative, is the limit of the change in variable approaching 0, right? Taken more and more infinitely precise, and then it's a slope of a line. So RT plus delta t minus RT, so that's like the rise over the run. Run is that change. So that's the limit definition. I don't know if Pearson's going to have you compute a derivative using this, but they do provide this because in last year's class, I took this definition and I proved the derivative. So we don't have time to do that today, but you could do it if you wanted to.
What would that look like visually? So for like you take the derivative and do that mention together, like their sign, which you can graph that. So what would that look like for 3 dimensions?
I'm going to answer your question with 2 things. First, the textbook has a really nice kind of like 3-dimensional graphic that I could never replicate on this whiteboard. But second, think of it kind of now, instead of a rise, with that difference of vectors, what you're really looking at is you've got a vector that's gone somewhere, then you're looking at another vector potentially changing in a different direction. We'll return to this idea in the curvature at the end of the chapter. So what you're doing is you're nudging time just a little bit to see how did my vector change with time. So potentially, like if you had a curve parameterized with t, and at this point time t1, you're going along like this, but then at this point t2, right now you're going down here like this. So change happens there, and there's lots of different ways to think of the change. Is it the change of that slope like I've modeled here? Or is it change if that's the origin of that position vector that's gone from here to there? And so this limit is then describing that rate of change as those 2 points get infinitely close together, but never the same. So that's kind of the start of the visual intuition if you wanted to construct that definition from scratch. But the textbook is able to put this in 3 dimensions. It's actually really pretty, so I'd recommend that if you can. Well, and in general, you're supposed to be reading your textbook at least allegedly, but it's week 2, so most of you have given up probably. So simply put though, like practically, you're not going to use this all the time. What you're going to do is if you're given R of t is equal to f of t, g of t, and h of t, then the way you compute the derivative is basically just copy paste 3 times. So f prime, g prime, h prime. That's very non-trivial. There's a proof that you can go through that, or just use it and know that you can do that. We call this something special. So we don't just call this a derivative. We call this a tangent vector. Who might guess where the word tangent is coming from?
The word tangent.
Yeah, because in Calc 1, tangent and slope were kind of taught to be synonymous. And so now we don't necessarily have slope because these curves are existing in, R3, but it is still tangent and it's a vector. So tangent, that's vector, tangent vector, it goes together. Okay, so let's do some examples. If I'm given R is equal to t cubed 3t squared and t cubed over 6, then R prime of t, what's going to be the first component here? Right, because we just differentiate that first component. So the derivative of that first component t cubed is just 3t squared. And so then the derivative of the second component, 3t squared, 16, not to be confused with 60, the number. And then t cubed over 6. Right, so the 3 is going to come down, cancel with the 6. So you have t squared over 2. And there you go.
Yeah.
So now you can take derivatives of vector value functions. Was that difficult? Okay, cool. If it was, you can ring up the Dr. Lang and retake Calc 1 while you're at it. I think I might post a derivative review, like just a master derivative rule sheet, because let's be honest, not everyone remembers the derivative of inverse arc cosine. So like, sure, go ahead and see it one more time, get it back in your memory.
That's 1 over x.
Because here's the thing, when I took Calc 3 as a student, I did not think, I was like, surely those obscure rules aren't going to be that important. Well, guess which rules were actually kind of important? In the places I didn't want them to be important, the inverse trigonometric derivative rules. So yeah, this is more than irrelevant all of a sudden. So I will post those. Yeah.
Both covers have all the rules on them, so maybe.
Oh, okay. Yeah.
Maybe.
And if not, they're probably listed somewhere earlier in the chapters. Yeah.
All my son and everything.
Okay, I'm going to show you guys that you can use. You're growing in something called mathematical maturity. So I'm gonna say the unit tangent vector. Okay, so what I'll tell you is that we denote this conventionally with capital T, but I want you guys to think about what this actually is going to be defined as. What are the 2 main important math words going on here in unit tangent vector?
Units and tangents.
What did we know about unit?
One.
Okay, one what? One nose hair?
Magnitude.
Right, the magnitude is 1.
1 unit in direction.
What does tangent mean?
Slow.
Yeah, essentially. And in the context of a tangent vector, what do we define a tangent vector as? Right, R prime, rate of change. So what do you think if we're taking the tangent vector, but we want the tangent vector as a unit tangent vector? What do you think it's gonna? What's the formula?
Divide by the magnitude.
Okay, so Mike, what's it gonna be?
Oh shoot.
Prime T.
So that's gonna be the square root.
Nope.
Okay.
At-
Albert,
Vector.
so
F prime
who
T.
remembers just generally what a unit vector? Well, so if you want to turn U into a unit vector,
Over
what do you
magnitude.
divide U by?
Magnitude of U.
Right?
Okay.
So if we have a tangent vector,
It's gonna
the
be
tangent vectors are prime. What do we want to divide the tangent? vector by?
magnitude of our magnitude.
Yes, the magnitude of itself. So this isn't really even a new concept. It basically takes what renaming r prime to the tangent vector, and then it recalls how we've been using unit vectors, and then it's boom, just turn it into a unit vector. So this is the unit vector, and it's a tangent, so it's a unit tangent. All good? So it's not trying to fool you. If you memorize that this is called the tangent vector, you'll really never really forget what this is. And so that's another reason why I don't believe in formula sheets. It's because it makes you think that everything's some sort of compartmentalized piece of information that's unrelated to each other. It's all related to each other, more intimately than even I'm letting on right now. But this is all you need to know, okay? So write that down. We're gonna run through a full exercise of that, just because it's gonna be really important for later. So it's worth seeing in a full application. And I have no doubt that Pearson will grind you to dust with exercises with these, so that's.
We finished next book. What did you say, Daniel? Seven to read it.
Okay, everyone follow very carefully along in your paper, because what I'm noticing is if I'm gonna cover an example problem in class, and one of you asks me, how did we solve that problem in class? That indicates that you just didn't write it down. Okay, so let's write it down, let's be efficient. Because time is a very rare commodity these days. Okay, so if R of t is equal to t squared 4t, and not 4 times the natural log of t, we want to find the unit tangent vector, okay? So the definition of unit tangent was going to be, there's a tangent vector involved, we should probably get that tangent vector, so r prime of t. The derivative of t squared is 2t, the derivative of 4t is just 4, and then the derivative of 4 times the natural log of t is 4 over t. And if that didn't come to you as quickly as I spoke it, then you are my target audience when I say review your Calc 1. Okay, so then we want the unit tangent vector though, so we need to find the magnitude of this. So the magnitude formula doesn't change just because we're using scalar valued functions instead of scalars by themselves. So this will be the square root, and we have 3 components. So we need to square each component and add them all together. So the 2t squared. We have the 4 squared, and we have 4 over t squared. So that's the magnitude formula applied to our tangent vector. And then we can simplify this. So it's the square root of 4t squared plus 16 plus 16 over t squared, which you should recognize pretty straightforward. This is just a square of a binomial, right? Because the 2t squared is giving the 4t squared, and then 4 over t is giving that when you expand. And then you can double check that 2 times 2t times 4 over t will cancel and you get 16 by itself. So then since this is squared, all that's left is the 2t plus 4 over t. So we're pretty much done. That's the hardest part of the problem, is getting your pieces. And now that we have the pieces, we can just invoke the definition. That's going to be r prime over the magnitude of r prime to make it unit. And in doing so, we can place our tangent vector 2t 4 over t over 2t plus 4 over t. This is a technically correct answer. I personally think this is just horrible to look at because of the fractions, but I won't waste your time with algebra that you're supposed to already know. So I'll show you the clean version that you could acceptably write this as. You could say t squared to t2 and t squared plus 2. So later on your own time, make sure you have the algebraic capacity to even make those things look the same. And if not, the displacement test is really helpful or things like that. Okay. Any questions about the procedure, definition, anything? Okay, so if you're given a vector value function and they ask for your unit tangent vector, you're telling me easy, got it, guaranteed solution.
I'm not gonna guarantee. But
Got it.
I'm gonna.
And again, this does rely, I am assuming you are familiar with your derivative rules. I am assuming that you are familiar with, high school algebra stuff. But assuming all of those things, we're good, right?
Yeah.
Okay. So let's move over to the derivative rules. Because there are a few specific product rules, because now with vectors, we have dot products and cross products. And you could specifically multiply a vector value function by a scalar value function. I have it all. I'll take a picture of this. Yep. I have it for that very reason. It's like insurance. Because I don't feel like writing it 5,000 times either. So I have one master copy.
Insurance.
I'm not going to show you the sum rule and because you know that if you have a linear combination, you just take the derivative, just take the derivatives through. So the ones that are different, this is going to be finally unique material that's different from Calc 1. So these derivative rules. So the chain, I'm gonna put the chain rule up here just because it's good to see why it's important to use good notation. So u is the vector value function, but you can put a scalar value function inside. Like so u, instead of just being u of t, you can be u of now f of t. And so that derivative is going to be very essentially analogous to the calculus 1 chain rule. But this is the vector, that's the scalar value function. If you mix those things together, you're going to run into issues. So be very careful about that. Okay, 3 product rules here. First kind of product, I like to call it a scalar product rule. So a scalar product rule. And that's where you're going to have dt, where f of t is acting as a scalar. It's a function, but it's a scalar quantity times the vector. And then, so this is an advancement of earlier when we would just take like a constant and multiply it by a vector, right? Now we're advancing it to being able to be parameterized, but the idea is still the same, constant vector. It's going to be analogous to all of these product rules are actually going to be analogous to each other. So it's f prime t u plus, that's a terrible plus sign, plus f of t times u prime. The way I like to say it, everyone gets a turn with the talking stick, where the talking stick is the derivative sign. So you'll just pair them up, and then everyone gets a turn.
And is this the case where f of t is a scalar?
Scalar, yes.
Okay.
Is there an arrow over it?
No.
Ah,
If there were arrows, how would that be done?
well, that's what these next 2 rules are for. Because there's 2 different ways you could do it with 2 vectors. The first way, you can do it with a dot product. So dot product. And that would be the derivative of u of t dot v of t. This is where I'll start to be picky about notation. If it's very obvious from context that you're doing scalars and you put a dot, I'm not going to be mad about that. I'll know what that is. But if you have vectors and then you just ambiguously throw multiplication symbols in there, I will read it as you are presenting it. Dots will mean dot products, crosses I will interpret as cross product. So dot, it's going to be exactly the same. Everybody gets turned with the derivative, but just make sure you use the correct multiplication. So here it's u prime of t dot v of t plus, and then now it's v's turn. So we get u of t dot v prime. Does that make sense when I say everybody gets a turn? Because if you think about that, you don't have to memorize anything. It becomes much easier. And so from here, you can actually write the cross product just by knowing what the pattern is going to look like. So try to write this on your own before looking up and checking your work with the whiteboard. So we're going to do the cross product between u and v. So the derivative of u of t cross v of t. I'll go quiet here for a little bit. Write it out so you get used to exercising the idea of everyone gets a turn, and then check your work with the whiteboard. And if you're feeling good, give me a thumbs up. There's lots of different kinds of products you'll find in mathematics. You're going to be using these three in Calc 3. And then if you move on to some algebra, some studies in algebra, you'll learn about 2 more products. And then topology, there's more products. But, okay, so we are all good. If I erase this, we're all fine? Okay.
Yeah.
While I'm erasing this, mentally verify all of these, not necessarily prove it, but see if you can just recall that pattern. Again, everyone has the talking stick once. I used to have students actually for the lab to prove the product, at least for dot products, like to prove that rule. I'm not going to make you guys do that, but it's interesting. But it's hard to convince engineers to do fun things, you know, like proving theorems, etc.
I don't like fun.
Well, I mean, you chose mechanical engineering, so. Oh,
Even less fun.
even less fun, yeah.
Exactly.
All right, so here is a notational definition. So integral r of t dt. We're going to, this is going to actually become really important in terms of the differences now between Calc 1 and Calc 3, is with the consideration of having vector valued stuff, I can't just say plus c a scalar anymore. That c's got to be a vector to accommodate the fact that there's going to be a constant for every single component, and all of those put together is going to form that component vector for the that arbitrary constant. So it's no longer arbitrary constant, it's an arbitrary vector formed where the components are those arbitrary constants from all the components individually. So in the same way that you saw that the limit could essentially be inserted into every single component, who's to say we can't do that with the antiderivative? So that's basically all that's going on.
What is that? Cross product or vector or t?
That's a plus. R of t dt.
Of dt.
Yeah, because it's an integral. Ooh, so you know, people are nice to the freshmen in Calc 1 and 2 because they don't want you guys to drop out and then they lose all funding for the department. But differentials are going to start to matter. So if you don't include a differential in your integral, that where it needs to be there, that's a problem. It's just wrong. And so then it'll be counted as such. You will have a pass when you get to Calc 4 and you start rigorously working through Darboux sums, because Darboux integrals don't come from a differential because it comes from set theory and infimums and supreme summation, but that's different. Here, we're not doing that. We need differentials, okay? Agreed?
Yes.
All right. So let's do an example because there's no, you don't need to hear me talk about indefinite integrals. Let's just do it. So if we're going to take the indefinite integral 1, 2t, 3t squared, dt. Ooh, differential, right? So that tells us where the integral stops. Now, you don't have to write this out every single time, but I'm going to do it now so you can see it at least once so you know what's going on. But this isn't like a prescriptive. If you don't show all these steps every single time, it's over. No, this is just so you can see conceptually what's happening. Essentially, we're going to do the integration for every single one of these with respect to dt. So it's going to be integral of 1 dt. And that x. And then the second component is going to be integral 2t dt. And then that 3t squared, dt squared dt. So in one sense, you can reconcile why are we allowed to just stick the dt on the outside? Because in one sense, it does distribute to every single component. The dt is found in every single one. So if you don't include the dt in the components, you wouldn't leave the dt on the outside. So the mistake would be to think that conceptually what's going on is that you've got the integral of 1, the integral of 2t, and the integral of 3t squared, and then somehow this is a dt. That's not good, okay? Because first of all, you just have integral sign. If you didn't put the 1 in there, nobody knows what that means, okay? So make sure that the dt's are paired up if you are going to express it this way. And then we're back to calc 1. So t plus the constant.
Oh, yeah.
Ooh, we've already forgotten. I'll find some really cringy boomer meme about plus c and I'll put it on the news item. Okay, 2t, right? C squared, please. And then we got this is dq. But so what happens, and the reason why we get this and generally conventionally the capital version of the lowercase letter is the antiderivative. It's a convention that's going to be used for differential equations as well.
Looks like PLC two, but like you said,
Well, these are arbitrary constants, and they're all different from each other. So I can't just put the same plus c plus c plus c because they don't have to be the same. They can all be different and arbitrary constants. And so then, using what we know about vectors, we can just split this apart. So we keep all of the t stuff going on. So t squared, t cubed. And then we can put together all of the constants, right? C1, C2, C3. And here's what you were allowed to always assume, okay? Regardless of how big the vector is, how many components you have, you can always just lump this and call that the vector C. So you can just say, like, this is a correct answer. This one would be marked wrong. It's just unnecessarily cumbersome. So you could just say t squared, t cubed plus c. And it's understood that those components are being gotten from here. But I wanted you to see what I really meant by this is a vector. That truly is a vector with components. Does that make sense? And so does that, this being a vector illuminated through this example where you go through each component? Because yes, it is very easy and sometimes convenient to forget about that constant, but it's important.
So you get two vectors from taking the vector? Oh, no, you get one.
No, it's one vector. So this is one vector. Because you could bring them together like this. So this is the singular representation, but we often split it up into the interesting part, and then we're not always interested in the constant. Does that make sense? Cool. Any questions about the indefinite integral kind of stuff? So basically, so long as you know your anti-derivatives, you're going to be fine. You're never going to be given an antiderivative that you haven't been taught in a previous class. Does that mean you still remember all the rules? No, but review them. I think I remember in the Pearson, one of the first textbook examples is the integral of 1 over 1 plus t squared, which is going to be now an inverse trigonometric, that's inverse tangent. And if you just don't know that, I'm sorry, you know, that's one thing that you got to memorize. So let's go over the last thing for today, which is the definite integral side of things. Let me erase this. And actually, we can let's reuse this function. And so definite integral is going to say, okay, well, let's just actually evaluate this on something. So these are understood to be t's, not x's, not anything from calc 1, because the variable is this parameter t, these are understood to be t. And so in that case, when you share it, you need to share every single part. Again, there's lots of parallel structure here. Nothing new. You just got to remember to do it. All good?
Mm-hmm.
So then when we actually compute this, what's happening is every single component is now just its own miniature calc 1 definite integral problem. So the antiderivative is t, like we know, but now we're evaluating t on 0 to 1. That becomes the component. So all of that can be contained in the component. You're allowed to do that. That's how you're supposed to do it. And before we finish fleshing this out, can you already conjecture what is going to be output from this definite integral of a vector value function? What's the very last thing going to be when simplified? It's going to be a scalar, or is it going to be a vector? Yeah. Is it going to be a vector is it going to be a vector valued function or a constant vector?
Constant
vector. That's what we're looking for. In the same way that when you take the antiderivative and you have plus c, but then if you were to take a definite integral like the area under a curve kind of a thing, you're just getting an actual number out. So here we got t squared evaluated 0 to 1, and then t cubed evaluated 0 to 1. Obviously, these numbers are intentionally easy because ridiculous arithmetic is a pet peeve of mine. You'll find that out pretty quickly. 1 minus 0 is 1, 1 squared minus 0 squared is 1, and 1 cubed minus 0 is 1. So the output is 1, 1, 1. So when you compute this definite integral over this vector valued function, you spit out a constant vector 1, 1, 1. Ooh. Okay. We've covered a lot of ground today. I mean, you've basically seen all of your old calculus, like the 3 pillars of calculus, but which applied to vector valued function. So it shouldn't be crazy. Here's my recommendation for you, okay? And I really do mean this, not just because I want you to succeed, but because I took this as a freshman and it was quite a learning curve, okay? So this is advice I would have given my past self. Get ahead in chapter 14, because the amount of new stuff here is the lowest it's going to be for the rest of the ride. It only goes like that, okay? So if you want to use chapter 14 to get behind so that you never catch up, that's your personal choice. But if I were you, if anything at the bare minimum, stay on top of chapter 14 and potentially use it to get a tiny bit ahead. Just so that when you hit the wall of chapter 15 and chapter 16, it doesn't wipe you out because it's about to go crazy. So make sure you don't slack on this chapter. It's easier content, so take advantage of the fact that it's easier content. Keep moving so that you don't lose any momentum when you start having to memorize much higher volumes of material. All good?
Yes.
I just want you to be aware of what's coming from personal experience. Okay, you guys all have a great day.